Welcome back to QHSE Talks. Imagine an AI system so perfect that it corrects factory errors before human operators even notice them.
Right.
Like, it seamlessly reads thousands of sensors, adjusts pressure valves in milliseconds, and, stops a chemical spill before a single drop hits the floor.
It sounds like magic, honestly.
Yeah, it sounds like an absolute safety utopia. But what happens when that flawless system inevitably glitches and the human operators suddenly realize they haven't manually driven the ship in 5 years?
That's the real problem.
Exactly. That is exactly the kind of paradox we are exploring today. If you are joining us, you are likely part of a very dedicated group of professionals, or you're just intensely curious about the hidden systems that keep the modern world functioning without, catastrophic failure.
Absolutely.
So today, we are directing our focus entirely on you, the listener. If you're preparing for your safety certifications, we were zeroing in on ASP 11, Domain 2, Topic 12.
Yeah, that is exactly right. For those tracking with the exam blueprint, Domain 2, Topic 12 mandates an in-depth awareness of emerging technologies.
Right, so we're talking about data mining, robotics, drones, and artificial intelligence.
Exactly. But let me set the parameters for our discussion right now, because understanding these technologies is not just an exercise in memorizing a list of shiny new gadgets to, check a box on a multiple choice test.
Right, it's way more than that.
It is. Knowing how these tools operate is an essential, non-negotiable skill for the modern safety professional to actually perform their duty in the field.
Because things are changing so fast on the ground.
Exactly. If you do not understand how an automated system fundamentally alters the hierarchy of hazard controls, you just cannot protect the workers interacting with it.
Yeah, and the stack of source material we're working with today is staggering. We are integrating the ASP examination blueprint, comprehensive study guides, the CCPS guidelines for risk-based process safety, and authoritative engineering texts like Roger L. Brower's Safety and Health for Engineers.
It's a lot to unpack.
It is. And what stands out immediately is how safety has evolved. I mean, we've gone from a paradigm of a lone inspector walking around with a clipboard and a static list of rules to a reality where we deploy drones to inspect invisible atmospheric hazards.
It really is a completely different landscape.
It's wild.
Yeah, but, while the landscape has evolved, the foundational laws of physics, thermodynamics, and human fallibility, they remain completely unchanged.
Right. Gravity doesn't care if you have an iPad.
Exactly. Gravity still pulls a worker down. Kinetic energy still crushes. Chemical reactions still occur.
Yes, basics never go away.
They don't. The core mission of anticipating risk and preventing the loss of human life remains constant. So our goal on this QHSE Talks is to figure out exactly how these new digital and mechanical tools interact with those ancient, unforgiving realities.
We really need to look at the mechanisms.
Yes, the physical mechanisms.
Okay, let's start with the mechanisms of data collection, because before we can have AI analyzing the factory, we have to actually capture the data.
Yeah, you need the inputs first.
Yeah. And when you read through Brower's work, it frames this technological evolution in incredibly stark terms. We have moved from these massive room-sized mainframe computers and literal warehouses of physical paper records.
Oh, the paper records were a nightmare.
Right. To a reality where tablets, smartphones, and memory devices the size of a fingernail hold encyclopedic volumes of process knowledge.
Yeah, the physical compression of information is basically the first domino in this evolution.
How so?
Well, let's look at how process safety information used to be handled. Decades ago, process knowledge like the exact chemical mixtures, the maintenance schedules, the structural blueprints was maintained in massive physical engineering files.
Which takes up a ton of space.
A huge amount of space. Or, even more dangerously, it existed solely as unwritten knowledge locked inside the heads of veteran employees.
Oh, wow. Yeah, that's terrifying.
It is. The texts note that historical information was basically limited to incident investigation records and equipment change logs. And because physical space is finite, companies would periodically purge those paper records just to make room in the filing cabinets.
Wait, they were literally throwing away their own safety history.
Yes, because they just didn't have the square footage.
And when you throw away your history, you are doomed to repeat it. That's crazy.
There's a massive vulnerability.
But now, the sheer portability of data fundamentally changes safety practices on the ground. The sources highlight documentation software that is completely upending the field programs like iAuditor and unsafe.
Yeah, those are game changers.
They really are. These applications allow safety professionals to conduct document and cross-reference complex audits directly on a smartphone while standing right next to the machinery.
Let's examine how that software mechanically changes the workflow, because that's the important part. We are talking about the acceleration of the observation to intervention cycle.
Okay, break that down for me.
Sure. So let's say it's 1995. A safety professional observes a frayed lifting strap on a crane. They write it on a clipboard. They finish their 3-hour facility tour.
Right.
They walk back to an administrative building, type up a paper report, print it out, and place it in a physical inbox for the maintenance supervisor, who might check it the next morning.
So the crane continues to operate with a compromised strap for another, 18 hours?
Exactly. The hazard is just sitting there fully active,
Yes.
while the paperwork slowly makes its way through the bureaucracy.
That's a huge window for a fatal accident.
Precisely. Now contrast that with the digital workflow outlined in the texts. You observe the frayed strap today, you open an application on a tablet, you take a high-definition geotagged photograph.
Which proves exactly where it is.
Right. And the software instantly maps that photo to the specific serial number of the crane in the relational database. It automatically generates a high-priority work order and pings the maintenance team's mobile devices before you have even walked away from the crane.
Oh, wow. So the intervention cycle shrinks from days to minutes.
Literally minutes. It's a totally different world.
It's not just the speed of the paperwork, though. The texts detail some incredible wearable technologies that take this a step further. We're looking at miniature sensors worn directly on a worker's lapel or belt.
Yeah, the wearables are fascinating.
Like, for example, noise dosimeters. In the practice materials, you constantly have to calculate time-weighted averages, figuring out the maximum time an employee can be exposed to an 86 decibel hum, or calculating the physical pressure exerted on an eardrum by a sudden 102 decibel impact noise.
Yeah, those calculations are notoriously complex. And to understand why these wearables are revolutionary, you have to understand the old method.
How did they used to do it?
Well, measuring noise exposure used to require a safety professional to stand next to a worker with a handheld sound level meter, manually taking static samples at different times of the day.
So just basically taking snapshots.
Exactly. And then you'd go back to the office to do complex logarithmic math to estimate the worker's total 8-hour exposure. It was an educated guess based on those snapshots.
But with a wearable dosimeter, you have a tiny piezoelectric microphone sitting right on the worker's shoulder.
Right next to their actual ear.
Yeah, and it's constantly listening, applying the OSHA-required awaiting network to mimic human hearing, and integrating that fluctuating noise level second by second for the entire shift.
It does all the complex logarithmic math continuously in real time.
That's amazing. And the sources note we are doing this with chemical exposures and pulmonary functions too, right?
We are. Workers wear badges with miniature photoionization detectors that can sense volatile organic compounds, or VOCs, in the parts per billion range.
Parts per billion, that's incredibly sensitive.
It is. If a worker enters a confined space and the oxygen level drops by even 0.5%, the wearable vibrates, flashes, and transmits an alarm to a central dashboard.
So we've effectively taken the analytical capabilities of a stationary laboratory and strapped them directly to the human body.
That's a perfect way to put it, yes.
Okay, so let me push back a little here. If we have these wearable laboratories and instant digital work orders, does just having a digital checklist or a sensor actually make a workplace safer?
What do you mean?
I mean, if a worker's wearing a smart badge but still ignores a safety protocol, hasn't the technology just allowed us to document the failure at the speed of light?
Ah, that is a great question. That gets to the absolute core of safety management, and it introduces a vital concept from the ASP blueprint, the difference between leading and lagging indicators.
Okay, leading versus lagging. Let's dig into that.
So the physical iPad, or the smart badge, is just a piece of plastic and silicon. Its actual value lies at how it transforms our safety metrics. Think about how safety was traditionally measured. We tracked the total recordable incident rate, the TRIR. We tracked lost time injuries. We tracked workers' compensation claims.
Right, but those are all lagging indicators. They only exist after someone has already been hurt.
Exactly. It's essentially an autopsy of a failed safety program.
Yeah, lagging indicators tell you how many people bled last month.
Right, which isn't very helpful for preventing the next injury. But the massive influx of real-time data from these mobile tools creates robust leading indicators. These are proactive metrics.
Because it's catching things before the injury.
Precisely. Because it is so easy to log a hazard on a phone, workers report hundreds of minor issues. A small oil drip, a missing label, a slightly loose handrail.
Stuff they wouldn't have bothered to write on a physical form.
Exactly. The friction to report is gone. So by aggregating thousands of these micro-observations, safety professionals can see a distinct trend of deteriorating conditions in a specific unit of the refinery weeks before the major blowout occurs.
Oh, that makes sense. So the speed of data collection allows us to shift from a reactive culture that investigates accidents to a proactive culture that investigates near misses.
That's exactly the shift.
Which means all this data is useless if it just sits in a digital filing cabinet. We have to process it. We're moving from simply storing information to actively mining it.
That is where data mining and expert systems enter the picture. When you aggregate millions of data points from those digital audits and wearable sensors, human analysts can no longer process the volume.
We just don't have the brain power.
We don't. The Handbook of OSHA Construction Safety and Health discusses how organizations use relational database management systems, or DBMS, to identify hidden trends.
Okay, but how does a relational database mechanically find a trend that a human would miss? I mean, practically speaking.
Well, think of a relational database as a series of highly interconnected spreadsheets. Let's say Table A tracks the specific serial numbers of respiratory protection masks. Table B tracks the training certifications of every employee.
Okay.
Table C logs the daily air quality monitoring results from different zones in the factory. And Table D tracks minor first aid visits to the on-site clinic.
So they're all separate silos of information.
Originally, yes. A human might notice that clinic visits for minor headaches are up. Another human might notice that Zone 4 has slightly elevated, but legally compliant, chemical vapor levels.
And a third person knows about the respirators.
Right. A third human knows that a specific batch of respirators was deployed last month. The human brain struggles to overlay all those variables across different departments.
Because they're not talking to each other.
Exactly. But a relational database can instantly cross-reference them. The data mining algorithm reveals that 80% of the workers reporting headaches were working in Zone 4 and specifically wearing that new batch of respirator.
Oh, wow.
Yeah, the system identifies a systemic failure in the personal protective equipment that was completely invisible when looking at the data points in isolation.
That's incredible. It acts like a digital centrifuge, spinning thousands of seemingly irrelevant daily data points until the heavy, dangerous hazard trends drop out to the bottom where we can actually see them.
That's a really good analogy.
And the texts point out that companies don't just do this internally anymore. They use internet data banks to track macro-level hazards.
Yes, they pull in external data streams.
Right. They're pulling in real-time tracking of seismic activity, weather patterns, national chemical pesticide recalls, and linking that global data right into their local facility dashboards.
It's extremely comprehensive.
Right.
But the CCPS guidelines for risk-based process safety look even further ahead. They envision a future where this data mining evolves into highly automated expert systems.
Okay, what does that look like?
The CCPS predicts that software will communicate directly with the BPCS, the Basic Process Control System, and the process data historians.
Okay, let's break that down because BPCS is a critical concept for the exam. What exactly is a basic process control system doing mechanically?
Imagine a massive chemical distillation column. The BPCS is the brain controlling the day-to-day operation. It uses proportional integral derivative controllers, or PID loops, to constantly read temperature sensors, pressure transmitters, and flow meters.
So it's making adjustments on the fly.
Right. If a pipe gets too hot, the BPCS automatically sends an electrical signal to open a cooling water valve. It regulates the process to keep it within safe operating limits.
And the data historian is just recording every single valve movement and temperature reading second by second, creating a massive digital archive of the plant's heartbeat.
Correct. Now, currently, human operators monitor these systems using large banks of screens in a control room. But humans are susceptible to alarm fatigue.
Oh, for sure.
When a minor pressure spike triggers a yellow warning light, and it happens 30 times a shift, the human operator learns to ignore it.
Yeah, it just becomes background noise.
Exactly. But the CCPS envisions an AI expert system that continuously analyzes the data historian. The AI doesn't get alarm fatigue. It notices that every Tuesday at 3:00 p.m., a specific pressure valve spikes by 4% for exactly 2 seconds.
A spike so fast and so small, a human would never register it as a threat.
Right. But the AI recognizes that this microscopic spike perfectly correlates with the exact moment a high-voltage pump on a completely different circuit kicks on.
Oh, I see where this is going.
Yeah, the AI identifies a harmonic vibration that is slowly degrading a critical pipe seal. It catches the near miss months before the seal ruptures. The system continuously monitors and corrects its own subtle deviations without human intervention.
Okay, so if the AI is acting as our digital centrifuge and it's catching the microscopic pressure spikes and filtering out the alarm fatigue, aren't we basically just outsourcing our safety awareness to an algorithm?
What's your concern there?
Well, if the computer is doing all the watching, what happens to the human operators? Do they just become passive bystanders, totally blind to the dangers around them?
That's a very valid concern. To answer that, we have to look directly at Domain 8 of the ASP Blueprint Human Factors Theory.
Which is all about how people interact with systems.
Right. Human factors theory is the scientific study of how human characteristics, cognitive abilities, and physical limitations interact with complex work environments. And the harsh reality of human neurobiology is that we have severe limitations when it comes to processing continuous, massive data streams.
We just zone out.
We do. We suffer from vigilance decrement. If you put a human in front of a radar screen and nothing happens for 4 hours, their brain literally stops actively searching for anomalies.
Yeah, we get bored, we get distracted. We're fundamentally wired to conserve cognitive energy.
Exactly. So the AI expert system does not replace safety awareness. It augments situational awareness by handling the tasks humans are biologically terrible at.
Okay, that makes sense.
By outsourcing the raw data processing and the vigilance to an algorithm that never sleeps and never loses focus, the safety professional is freed up to utilize the skills that AI completely lacks.
Like what?
Like context, emotional intelligence, and cultural understanding.
Oh, I get it. So the AI tells you that a specific safety interlock on a machine has been bypassed 14 times this week. It gives you the what?
Yes, and then the human safety professional walks out to the floor to figure out the why.
Right, the AI can't interview the worker.
Exactly. The human talks to the operators and realizes the ergonomic design of the machine forces the worker into a painful, awkward posture unless they bypass the interlock.
So the root cause was ergonomic, not behavioral.
Precisely. The AI found the data anomaly, but only the human could identify the ergonomic root cause and redesign the workstation. AI handles the volume, humans handle the context.
That makes total sense. We use the digital tools to process the invisible data. But AI doesn't have hands. It doesn't have physical form. For technology to physically interact with the real world, we have to move from software to hardware.
Yes, into the physical environment.
Let's look at how we deploy these tools into the physical environment, starting with the sky. Let's talk about drones.
Unmanned aerial vehicles, or UAVs. The text explicitly detail their use in facility evaluation, materials handling, and surveillance.
They're everywhere now.
They are, and they are transitioning from novelties to absolute necessities in heavy industry because they fundamentally alter human exposure to kinetic and gravitational hazards.
The Safety Professionals Reference and Study Guide provides a perfect scenario for this. Imagine a massive industrial facility with a 150-foot-tall chemical storage silo.
Okay, yep.
At the very top of that silo, there's an analog pressure gauge or a structural weld that requires a visual inspection every single month.
So let's walk through the mechanics of the traditional method for that inspection. It is a high-risk, multi-hour operation.
Right.
First, the worker must review the job safety analysis. They must inspect their personal fall arrest system, checking the harness stitching for chemical degradation, ensuring the dual-leg shock-absorbing lanyards are intact.
And they have to do math.
Yes, they must calculate their fall clearance. They have to review the weather, checking for high winds or lightning risks, and only then they begin the grueling physical exertion of climbing 150 feet of vertical caged ladder.
Which is exhausting. They are completely exposed to gravity, cardiovascular fatigue, potential slip hazards from morning dew on the metal rungs, and, the psychological stress of the height.
It's incredibly dangerous.
And as safety professionals, we try to manage that risk. We require 100% tie-off. We give them the best PPE. We mandate rescue plans.
But look at the hierarchy of hazard controls, which is Domain 2, Topic 2, by the way. The hierarchy ranks controls from most effective to least effective.
Right, the pyramid.
Exactly.
Yeah.
At the bottom is PPE, like the fall harness.
Yeah.
Above that are administrative controls, like the climbing permit. Above that, engineering controls, like the ladder cage. Above that, substitution. And at the absolute pinnacle is elimination.
Removing the hazard entirely.
Exactly. When you deploy a drone equipped with a 4K camera and a telephoto lens, the safety professional stands firmly on the ground, flies the drone up to the gauge, captures the data, and lands.
Wow. So you haven't mitigated the fall hazard with a harness, you have achieved elimination.
Yes, gravity has been completely erased from the risk equation because the human never leaves the Earth.
It's the ultimate engineering control. But wait, if we are sending a spinning piece of plastic and lithium-ion batteries into a highly sensitive chemical environment, aren't we just trading a fall hazard for a whole new set of technological hazards?
Oh,
I
absolutely.
mean, what happens when the drone fails?
Your skepticism is exactly what the study guides demand of a safety professional. You never get a free pass on risk. This introduces the absolute necessity of a dynamic risk matrix.
So you have to reevaluate.
Yes. When you eliminate the fall hazard by introducing the drone, you must immediately conduct a new hazard analysis for the UAV itself.
Okay, let's break down those new drone hazards mechanically. First, you have the power source. Drones rely on high-density lithium-ion polymer batteries.
And those are notoriously volatile.
Right. If that drone strikes a pipe and fractures the battery casing, the internal separator between the anode and cathode is compromised. You get an internal short circuit leading to thermal runaway.
Which is an incredibly intense fire.
Exactly. The battery violently combusts, projecting sparks and toxic gases. If you're flying that drone over a combustible dust area or a volatile vapor cloud, you have just introduced a catastrophic ignition source.
That's a huge risk. Then you have the mechanical hazards. A drone weighing 10 pounds falling from 150 feet becomes a deadly dropped object.
A 10-pound weight falling that fast could easily kill someone.
Exactly. So you have to establish exclusion zones on the ground underneath the flight path, which requires new administrative controls.
And what about signal interference? Industrial plants are a nightmare of electromagnetic noise.
Oh, they definitely are.
You have massive high-voltage transformers, thousands of pounds of steel structure creating Faraday cages, and localized Wi-Fi networks everywhere. The drone pilot's 2.4 gigahertz radio signal could be attenuated or completely blocked.
Causing the drone to lose its command link and crash into a critical piece of infrastructure.
Right, so it's not a magic bullet.
No, which is why safety is a continuous, never-ending loop. The drone is an incredible tool that achieves hazard elimination for the worker, but it simultaneously introduces kinetic, electrical, and thermal hazards.
Which all have to be managed.
Managed through strict pre-flight checklists, intrinsically safe drone models, and rigorous pilot competency training. You don't eliminate risk, you manage its transformation.
You manage its transformation. I like that. So we have flying robots managing risk in the air. But automation is also happening right on the factory floor, working shoulder to shoulder with humans.
Yes, industrial robotics.
How do we manage the mechanical hazards when the robot isn't 150 feet in the air, but sitting right next to the assembly line?
Well, this is where we get into a truly fascinating application highlighted in the sources, the biohazard buffer.
The biohazard buffer.
Yes. Brower's engineering text details how robotic arms, placed inside sealed enclosures and operated via remote control or programmed logic, are used to process dangerous biological samples or highly toxic radioactive materials.
So the robot serves as a physical proxy.
Exactly. The human stands safely behind a barrier, and the mechanical arm handles the pathogen. The robot itself is the safety control.
It acts as an absolute buffer, but the OSHA regulations detailed in the study guides make it incredibly clear. You cannot just bolt a 6-axis robotic arm to a table, plug it in, and assume your workers are safe.
Not at all.
The sheer kinetic force of an industrial robot, its speed, its blind spots, its unyielding torque, makes it one of the most dangerous pieces of equipment in a facility.
It will crush a human without even slowing down.
So how does OSHA mandate we protect the workers from the machine that is supposed to be protecting them?
The regulations require a rigorous, multi-layered approach. First is the comprehensive risk assessment, analyzing the robot's entire envelope of motion, its maximum range.
Okay, so you map out everywhere it could possibly hit.
Right. Second is specialized training for the operators and programmers. But the third point is the most mechanically critical: the installation of safeguarding and interlocking mechanisms.
Okay, let's explain how an interlock actually functions. It's not just a warning sign on a door, right?
No. An interlock is a physical, fail-to-safe engineering control. Imagine the robotic arm is inside a cage. To access the robot, a worker must open a heavy metal gate. Attached to that gate is a coded magnetic safety switch. This switch is directly wired into the robot's main power contactors. When the gate is closed, the magnetic field is complete, the circuit is closed, and the robot operates.
But the millisecond the worker pulls that gate open,
The magnetic field breaks, the safety relay instantly drops out, physically severing the electrical power to the robot's drive motors and applying emergency mechanical brakes to its joints.
Wow, so the robot freezes instantly.
Instantly. It is mechanically impossible for the robot to move while the gate is open. This ensures the worker can never share the space with an energized, moving machine.
And the texts mention the requirement for emergency stop or e-stop buttons. These aren't just pause buttons on a keyboard, are they?
No. A true e-stop overrides all software controls, directly cutting hardware power to stop hazardous motion immediately.
Exactly. You also have requirements for routine maintenance inspections, specific PPE, and strict record keeping.
Right. All crucial layers of defense.
But wait, think about this. If the robot breaks down, say, a hydraulic line bursts inside the arm, a maintenance worker has to go inside that enclosure to fix it.
They do?
The gate is open, so the interlock prevents the robot from running its normal program. But the maintenance worker still needs to interact with the machine's internal components. Who protects the protector?
This brings us to one of the most critical foundational programs in all of safety engineering, lockout to gout, or ELOTO-HO, which controls hazardous energy.
Yes, ELOTO is huge on the exam.
The interlock on the door is for normal operations, but for maintenance, the worker must completely isolate the machine from all energy sources.
And it's not just electrical energy. We're talking about pneumatics, hydraulics, thermal energy, gravity.
Precisely. To safely maintain that robot, the worker must follow a strict sequential procedure. They turn off the main electrical disconnect switch and place a physical padlock through the switch handle, keeping the only key in their pocket.
So nobody can accidentally turn it on.
Right. Then they must locate the pneumatic valves that supply compressed air to the robot's grippers. They close those valves, lock them, and open a bleed valve to release any residual air pressure trapped in the lines.
Because even trapped air can cause the arm to jerk.
Exactly. And if the robotic arm is suspended in the air, they must install physical blocking pins to prevent gravity from pulling the heavy arm down if a hydraulic cylinder fails.
They basically have to methodically bleed the machine of every ounce of potential and kinetic energy.
Yes, they do. The robot mitigates the biological hazard. The interlock protects the operator from the robot, and the lockout and cow-out program protects the maintenance technician from the stored energy.
It's a chain of protection.
It is, and if any single link fails, if a worker decides to skip the padlock because, it'll only take a second to fix, the kinetic energy of that robot will crush them.
It's incredible how the new technology, the advanced robotics, forces us to rely so heavily on the oldest, most fundamental administrative controls like ELOTO.
The fundamentals never change.
So true. But automation isn't just confined to the factory floor or the laboratory. It is driving out the loading dock doors and hitting the open road. Let's look at fleet safety and telematics.
Right. Telematics and the automation of vehicles represent a massive transformation in public and industrial safety. The sources detail how complex surveillance equipment is now standard issue in commercial fleets.
We aren't just talking about a GPS dot on a map anymore, are we?
No, we are talking about electronic logging devices, or ELDs.
Yeah.
This is a massive shift in fatigue management.
Okay, let's talk about that. Historically, commercial drivers tracked their hours of service using paper logbooks. Drivers were limited by law to a certain number of driving hours before a mandatory rest period.
Right.
But those paper logs were infamously referred to as comic books.
Because they were essentially works of fiction.
Exactly. A dispatcher would pressure a driver to make a delivery, and the driver would falsify the paper log to hide the fact that they had been driving for 16 hours straight.
And fatigue is one of the deadliest hazards on the highway.
So the administrative control of the paper log was entirely reliant on the honor system.
Right. But the ELD changes the mechanics of compliance. An ELD physically plugs into the commercial truck's engine control module, the ECM.
So it's tied directly into the brain of the truck.
It is. It reads the raw telemetry of the vehicle. It knows the exact RPM of the engine, the speed of the wheels, the odometer reading, and the GPS location. The moment that truck moves faster than 5 miles per hour, the ELD automatically switches the driver's status to driving.
Wow, you cannot spoof the engine telemetry.
You can't. It replaces a fragile administrative control with a hard, data-driven engineering control. But telematics go much deeper than that.
How so?
Well, fleets use intelligent dash cams equipped with inertial measurement units, G-force sensors. If a truck suddenly brakes hard or swerves, the sensor detects the extreme G-force and automatically saves the video footage from 10 seconds before the event to 10 seconds after.
Oh, that's brilliant.
Yeah, and it instantly uploads that clip to the safety manager.
And the software uses machine learning to analyze the video inside the cab too, right?
Yes, the driver-facing cameras.
It can detect if the driver's holding a cell phone, if they aren't wearing a seatbelt, or even if their eyelids are drooping, triggering an audible alarm in the cab to wake them up.
It's incredibly proactive.
We also have blind spot radar detection and continuous tire pressure monitoring systems that alert the driver to a slow leak long before the tire suffers a catastrophic blowout at 70 miles per hour.
These telematic tools are saving lives daily. But the texts push us further into the realm of fully autonomous vehicles.
Okay, self-driving trucks.
Yes, we're talking about machines operating as multi-ton robots. They utilize LiDAR, light detection, and ranging.
How does LiDAR actually map the world, like physically?
A spinning sensor on the roof of the vehicle fires millions of laser pulses per second in a 360-degree arc. It measures the exact time it takes for those light pulses to bounce off objects and return to the sensor.
So it's basically echolocation, but with lasers.
Exactly. By calculating the speed of light and the return time, the computer builds a highly accurate, real-time 3D point cloud of its environment. It knows exactly where the pedestrians, the other cars, and the guardrails are, down to the millimeter.
Even in the dark.
Even in pitch darkness.
That's wild. The sources mention that this technology is incredibly beneficial in highly hazardous environments, like open pit mining.
Oh, it's perfect for mining.
Instead of putting a human driver in a massive dump truck that is 3 stories tall, navigating treacherous, muddy, unstable off-road terrain, you use autonomous haulage systems.
Because the computers never get tired, they never get distracted, and they execute the route with mathematical precision, removing the human entirely from the rollover hazard.
But here is where we slam into what safety engineers call the automation paradox. And the texts use a deeply unsettling historical example from the commercial airline industry to illustrate this danger.
Yeah, let's explore that paradox because it's crucial.
Decades ago, the aviation industry pioneered highly advanced automated flight management systems. Commercial aircraft essentially fly themselves from shortly after takeoff to shortly before landing.
The computers manage the throttle, the navigation, the fuel mixture.
Right, and the flight becomes incredibly smooth, efficient, and statistically vastly safer.
So what's the problem? I mean, that sounds like a total success.
Well, the unintended consequence revealed itself during preliminary investigations into complex aircraft accidents. Because the autopilot is so reliable, commercial pilots fly completely automated routes day after day, year after year.
The computer does 99% of the flying.
Exactly. But because the pilots are no longer manually manipulating the yoke, feeling the aerodynamics of the plane, and manually correcting wind shear on a daily basis, they suffer from a phenomenon known as skill fade.
Skill fade. So their raw stick and rudder flying skills slowly atrophy from lack of use.
Exactly. The paradox is this. The more reliable the automated system is, the less the human operator practices. But humans are fundamentally terrible at being passive monitors.
We zone out.
We zone out. So when that highly reliable system encounters a scenario it wasn't programmed for, say, a completely unprecedented weather anomaly freezes the pitot tubes, and the autopilot suddenly disengages and hands manual control back to the pilots.
Oh, man.
The pilots are suddenly thrust into a chaotic life-or-death crisis, alarms are screaming, the plane is stalling, and they haven't manually recovered a heavy jet from a high-altitude stall in 5 years.
And that is exactly what happened in several tragic aviation accidents. The pilots reacted with incorrect manual inputs because their intuitive muscle memory skills had faded.
It's terrifying.
We identify a hazard human error in driving or flying, and we fix it by automating the process. But the automation breeds complacency, creating a new hidden hazard. When the machine fails, the human fallback is completely degraded.
So how on earth does a safety professional combat the automation paradox? Do we just turn the computers off?
No, the computers save far too many lives. The answer lies in Domain 8. Training, education, and communication. This is why defining baseline competencies is critical.
We can't just train them to push buttons anymore.
Exactly. We can no longer train workers just to monitor the glowing screens and push the start automation button. We must actively, relentlessly train them for the exact moment the technology fails.
We have to force them into simulators. We have to make them manually drive the mining truck or manually run the chemical process in a safe training environment on a regular basis, intentionally maintaining those perishable skills.
Yes. We have to train them for the worst-case scenario that the machine is specifically designed to prevent.
Precisely. You must ensure that the human can always act as the ultimate manual override. And this theme of, unknown and unintended risks from new technologies sets us up perfectly to discuss the bleeding edge of emerging tech: 3D printing, nanomaterials, and unforeseen hazards.
The pace of innovation in materials science is breathtaking right now. Let's start with 3D printing, or additive manufacturing. The technology is rapidly dropping in price and expanding into every sector.
It really is.
Instead of traditional subtractive manufacturing, where you take a block of steel and use a lathe to carve away material until you have a part, 3D printing builds objects layer by layer from the ground up.
And the texts note the incredible versatility of this. Fused deposition modeling uses heated nozzles to extrude melted plastics like ABS and PLA.
Right, the plastic filament printers.
Then selective laser sintering uses high-powered lasers to melt and fuse microscopic beds of metal powder into solid titanium or aluminum parts. They're even beginning to 3D print biological materials and artificial tissues.
It truly sounds like science fiction. You just download a digital file and print a complex mechanical valve. But the safety and industrial hygiene challenges are an absolute nightmare, because you aren't just dealing with one hazard.
Let's break down the hazard profile of a 3D printer. First, you have the mechanical and thermal hazards of the machine itself.
You have rapidly moving gantries creating pinch points.
Right. And extruder nozzles operating at hundreds of degrees Celsius, introducing severe burn risks.
And second, you have the chemical hazards of the raw materials. When you superheat and extrude plastics, you don't just get a bad smell. You are releasing volatile organic compounds and ultrafine particles, or UFPs, directly into the worker's breathing zone.
So if a facility just places a bank of 3D printers on office desks without localized exhaust ventilation, they're continuously poisoning the indoor air quality.
They absolutely are. And if you're using metal powders for laser sintering, you introduce one of the most terrifying hazards in manufacturing: combustible dust.
Oh, combustible dust is no joke.
It's not. Powders like titanium or aluminum, when suspended in the air in the right concentration, can ignite with explosive force.
A simple static spark from an ungrounded vacuum cleaner cleaning up spilled powder can trigger a catastrophic deflagration that levels the room.
Literally blows the roof off the building. And finally, you have the structural hazards of the printed object itself.
Let's talk about that. If I use a traditional lathe to carve a bracket out of a solid block of forged steel, I know its structural integrity.
Because it's a solid block.
Right. But if I 3D print that same load-bearing bracket layer by layer, how do I know the laser perfectly fused every single microscopic layer? What if there is a tiny invisible void deep inside the print?
You wouldn't be able to see it.
Exactly. When I bolt that bracket to a crane, it might snap under half its rated load, dropping a payload on a worker.
The quality assurance and non-destructive testing protocols have to be entirely reinvented for additive manufacturing. And alongside 3D printing, the texts emphasize the explosive rise of nanomaterials.
Nanotechnology. We are talking about materials engineered at the atomic or molecular scale between 1 and 100 nanometers.
To put that in perspective, a sheet of paper is about 100,000 nanometers thick.
Wow. The critical concept to understand here is that when you shrink materials to the nanoscale, the fundamental laws of physics and chemistry begin to shift.
They behave totally differently.
Nanoparticles have a massive surface area to volume ratio. A chunk of gold is inert and safe to hold. But nanoscale gold particles can become highly reactive and toxic.
The National Institute for Occupational Safety and Health, NOH, has had to scramble to develop entirely new strategies for handling these materials. Because they are so small, they don't behave like normal dust.
They behave almost like a gas.
They do. Traditional mechanical filters might not capture them. Furthermore, because of their microscopic size, if a worker inhales carbon nanotubes, the particles can penetrate deep into the alveolar region of the lungs.
That's horrifying.
It gets worse. Some studies suggest certain carbon nanotubes, because of their rigid, needle-like shape, interact with lung tissue in ways eerily similar to asbestos fibers.
Like mesothelioma.
Yes, potentially causing severe pulmonary fibrosis. Or mesothelioma. They can even cross the blood-brain barrier.
The texts use a brilliant historical anchor to put this terrifying unknown into perspective. They look back at the semiconductor industry in the 1980s and 90s.
It is the perfect cautionary tale. When cleanroom technology was first developed for manufacturing silicon microchips, it visually looked like the safest industry in human history.
It looked pristine.
The rooms were absolutely spotless, bathed in yellow light. The workers wore head-to-toe bunny suits. The air was scrubbed through massive HEPA filters.
It looked like a sterile hospital operating room.
But the reality was entirely different. The pristine environment was designed to protect the microchips from human skin cells and dust.
Wait, it wasn't for the humans.
No. It was not designed to protect the humans from the highly exotic, unstudied chemicals and solvents being used to etch the silicon. Over time, epidemiological studies revealed severe, unexpected long-term health effects, elevated cancer rates, reproductive issues that weren't immediately apparent.
The visually spotless environment masked a highly toxic reality.
Exactly. Nanomaterials and 3D printing represent today's version of that semiconductor unknown.
It's like a technological Trojan horse. It arrives looking flawless, sleek, and highly advanced on the outside, but it harbors entirely new, microscopic, scientifically unstudied risks on the inside.
That's exactly what it is.
So, what is the strategy? How does a safety professional protect a workforce from a hazard the global scientific community barely understands yet?
You return to the foundational principles of engineering, specifically prevention through design, or PTD, and you cultivate what the CCPS calls corporate memory.
Let's tackle PTD first because it is heavily tested and practically essential.
Right. Prevention through design is the philosophy of anticipating and engineering hazards out of a process during the earliest conceptual design phase, long before a facility is built or a machine is purchased.
The texts provide a fantastic example of PTD in action at a biofuel facility. The original facility design required workers to conduct a monthly washdown of large processing tanks.
Okay.
To do this, the workers had to physically drag 300 feet of heavy pressurized vacuum hose up multiple flights of metal stairs.
Let's analyze the hazard profile of that task. You have massive ergonomic hazards from lifting the hose. You have severe slip, trip, and fall hazards from dragging wet hoses across metal grating on stairs.
The old-school safety approach would be to focus on the worker. We would train them on proper lifting techniques. We would require high-traction boots. We would put warning signs on the stairs.
But all of those are low-level administrative and PPE controls. They don't change the physical reality of the heavy hose on the stairs.
Prevention through design takes a completely different approach. When that company built their next facility, safety engineers were involved in the blueprint phase.
That's the key.
Instead of requiring the dragging of hoses, they designed a built-in standpipe system that ran vertically up the side of the building with quick connect ports installed on every single level.
So now the worker just walks empty-handed up the stairs, grabs a short 15-foot lightweight hose stored on that level, and plugs it into the wall port.
Exactly. The ergonomic hazard and the trip hazard are permanently engineered out of existence. The hazard was eliminated before the concrete was even poured.
That's PTD at its best. Now apply PTD to our Trojan horses, 3D printing and nanomaterials. Safety professionals must demand a seat at the table during the procurement phase.
Before they even buy the machines.
Yes. Before the company buys the 3D printers, the safety professional ensures the architect designs a dedicated room with negative air pressure and specialized localized exhaust ventilation routed directly to the outside.
And before the lab orders a new nanomaterial, you analyze if there is a bulk material substitute.
Exactly. You build the enclosures and the capture systems before the hazard ever arrives in the loading dock.
You anticipate the unknown, but to anticipate the unknown, you have to remember the past. What about corporate memory?
The CCPS text issues a stern warning about a prevalent, dangerous trend in modern industry: the loss of corporate memory. Experience is a powerful, albeit brutal, teacher.
It is.
But the painful lessons learned from watershed disaster events, like the semiconductor chemical exposures, the Bhopal gas tragedy, or the Deepwater Horizon, are all too quickly forgotten if an organization does not deliberately, systematically decide to remember them.
Because the workforce turns over, the veteran engineers retire and take 40 years of unwritten context with them. Management changes hands, and the new executives look at the complex, expensive safety protocols and just see unnecessary red tape slowing down production.
Precisely. The new generation doesn't know why the rule was written in blood. That is why the CCPS highly recommends appointing technology stewards, dedicated personnel whose job is to maintain process knowledge, document the engineering rationale behind safety systems, and ensure that historical data is retrievable.
So they are the keepers of the history.
Yes. A company must deliberately nurture a safety culture that respects the unknown. You have to actively remember the painful lessons of the past and apply that hardened skepticism to every new technological marvel that is supposed to make everything perfectly safe.
Let's take a breath and zoom out to look at the incredible ground we have covered today. For you listening, we have traveled from the era of dragging paper clipboards and relying on lagging indicators to a world where wearable dosimeters calculate logarithmic noise exposures in real time and iPads trigger instant maintenance and preventions.
It's been quite a journey. We examined how relational databases act as digital centrifuges, spinning massive data sets to reveal hidden near-miss trends. We explored the CCPS vision of AI expert systems communicating directly with process control loops to correct microscopic deviations before they escalate.
We looked at how drones operate at the absolute pinnacle of the hierarchy of controls, completely eliminating fall hazards by removing the human from gravity, while simultaneously demanding we update our dynamic risk matrices to account for lithium-ion battery fires and kinetic impacts.
We broke down the OSHA regulations surrounding industrial robotics, detailing how physical interlocks provide a biohazard buffer, but also how rigorous lockout-tagout procedures are the only thing protecting the maintenance technician from the stored energy of the machine itself.
We tackled fleet telematics, from ELDs enforcing hours of service to LiDAR-guided autonomous mining trucks. And we unpacked the chilling reality of the automation paradox and skill fade. The understanding that highly reliable automated systems make humans terrible passive monitors, making rigorous worst-case scenario simulator training more essential than ever.
Finally, we peered into the atomic-level uncertainties of 3D printing and nanomaterials, applying the principles of prevention through design to engineer out respiratory and combustible dust hazards before they exist, and stressing the vital importance of maintaining corporate memory so we never forget the hard-learned lessons of the past.
The ultimate takeaway for your professional practice and for the ASP exam is this. It is not about knowing how to code the AI algorithm or solder the wiring on the drone.
No, it's not.
It is about understanding how that technology fundamentally shifts the physics and the psychology of the hazard landscape, and knowing how to apply foundational safety engineering to those new complex environments. What is the final lingering thought we want to leave our listeners with today?
It circles back to the very beginning, to that CCPS vision of the future. They envision a plant where expert systems seamlessly process data, identify subtle near misses, and perfectly correct mechanical failures without any human intervention.
The utopia.
Right. But consider the deep psychological impact of that perfection. If an AI system flawlessly corrects itself 99.9% of the time, keeping the facility perfectly quiet and safe day in and day out, does that breed a culture of complete systemic human complacency?
Oh, wow.
When the 0.1% event finally occurs, the unprecedented cascading black swan event that the AI was never programmed to recognize because it has never happened before, will the human operators have lost the raw safety intuition, the panic response training, and the sheer ingenuity required to manually save the facility?
Will the perfect machine ultimately create the imperfect human? That is a profound and chilling question to ponder as we continue to build these technological utopias. Thank you so much for joining us on this depth exploration. Take a look around your own workplace today. Look at the glowing screens, the automated valves, the wearable sensors, and the robotic arms, and ask yourself, what are my smartest tools hiding from me, and what happens when they go dark? Stay safe, keep questioning the systems around you, and we will catch you on the next QHSE Talks.